Having talked about a formal definition of a limit, a very important application is to the limit that we get to if ultimately we create the expression 0 over 0. Now, why this is a problem is if we think of the fraction 0 over k, where k is not 0, that value is always 0. Now, if we think of a related fraction where we have k is some number but not 0 over a very small number close to 0, then that k over a number very close to 0 becomes a very large number, or it's far from 0. So 0 over k is 0, and k over a very small number is a very large number. Thinking about this, what's the value of 0 over 0? The two behaviours are sort of pulling in the opposite direction. So basically, we say that the value 0 over 0 is indeterminate. We can't give it a value. And why are we interested in that? Because in calculus, we often arrive at the expression some function over another function. And if for some input value x, both the functions are getting closer to 0, then that ratio can be anything. And that will come up in differentiation, particularly sine x over x. Now it turns out, we'll show later, that that limit is equal to 1, even though the value of sine x and x at 0 is both 0. Now, if we take x in this expression and make it closer to 0, look at the value of the ratio. Okay. Let's look at x squared minus 1 over x minus 1 as x tends to 1. As x tends to 1, both the top and the bottom, the numerator and the denominator, are getting closer to 0. But the value of their ratio is getting closer to 2. For x squared over x, if we make x getting closer to 0, we say the value of the ratio is getting bigger and bigger. And finally, 1 minus cos h over h, as h tends to 0, at h equals 0, that is 0 over 0. But if we put in values of h that are getting closer to 0, the ratio is getting closer to 0. We can have different expressions where the value at a certain input value of the ratio would be 0 over 0, but the actual ratio as we're getting closer is getting closer to different values. 1, 2, infinite, and 0. So here, these are 4 examples that show even if our ratio is tending towards 0 over 0, the actual limit can be a different value in different situations. And you have to apply other techniques to find out what that limit is. Why it's important is because it occurs in differentiation from first principles as a way to find out the derivative of a function. After having been through that, try and answer why is 0 over 0 indeterminate? What other indeterminate forms exist? And try and explain why the statement both the top and the bottom go to 0, so the limit is 0, is incorrect. So after this introduction, we'll go into more formal mathematics of limits.